Hello everyone, good day. In this video, we are going to see the concepts of Kubernetes Service Networking. If you like this video, please subscribe to VSPARKZ channel and click the bell icon for the latest updates. This is the agenda of this video. We are going to discuss on these topics in this video. Recap Kubernetes Networking. In the previous videos, we have divided the Kubernetes networking model into two divisions, that is Kubernetes cluster communication and Kubernetes objects communication. Today, we are going to discuss on how the Kubernetes objects like pods and services communicates with each other. Problems with pod networking. Let us first understand why we need to go for Kubernetes services. Consider a Kubernetes cluster having 3 nodes and it is connected to the physical network using the bridged networking model. All these bridges forms a cluster-wide global network called the overlay network. Now assume that we are deploying our workloads in the form of pods. For example, a web server pod and a database pod in our case. Every pod will be getting an unique IP address based on the bridged network that it is attached to. To access our web application, we will be using the web server's pod IP in our clients. So, whenever this pod IP is hit in a desired port, we will be able to access the web page which is served by the web server within the pod. Similarly, to access our database, we will be using the database pod IPs. Now, coming to the actual problem. As we all know, pods are ephemeral and it can be destroyed and recreated at any point in time by Kubernetes. We should not expect that an individual pod will be reliable and durable as they are very dynamic. This can be due to many reasons, and one such valid reason is node failure. Whenever a node gets crashed or not available due to network issues, the pod that is running in that node will be killed and rescheduled in another available node. When it is scheduled in another node, the original pod IP gets changed according to the current bridged network. So, when the client tries to access the old pod IP, it won't get any response from the web server as the pod is moved out to a new bridged network with a new IP address. In this case, the client needs to update it to the current pod IP for accessing the web server. Again, after some time, this node can also be crashed. So it is really hard to hardcode the pod IP address in the clients for accessing our applications. Then how to solve this problem? And the solution is Kubernetes Services. Kubernetes Services. Let us understand what Kubernetes Services are. Kubernetes Services provides an abstraction layer on top of our application deployments that is running as one or more pods in our cluster. Kubernetes Services actually connect a set of pods to an abstracted IP address and a service name. Let us consider the same example from the previous slide where we are running our web server application in the form of pods. Assume that the application is deployed in the form of Kubernetes deployments with 3 replicas. Once we create a service on top of this, it helps to expose these group of pods over a network. In other words, this service is an abstracted layer for the web server pods. Services will be assigned a unique IP address once it is created. This unique IP address is a static IP address and it is not changeable until we delete and recreate the service. There are many types of services available, but for this use case, let us assume it as a cluster IP type and it is resolvable only within the cluster. Now our clients needs to hit only this static service IP. Once this service is hit, it will just forward the incoming traffic to the backend endpoints. In this case, the endpoints are nothing but the pods. If any of the pods is killed and created with a new pod IP, the service will automatically update its database with the new pod IP. So, with this mechanism, the earlier problem with the pod networking is resolved as we have got a static IP from the Kubernetes services. Now, let us understand how this service works a bit more in detail. How service works. Let us take a typical cluster where we can see many pods that are running our applications like web server, databases, etc. Kindly note that every pod will be having its own labels. We are going to see the importance of these labels in a minute. Assume that we need to expose the web server workloads over the network, and so we will be creating a Kubernetes services to expose the same. The common question that arises here is, how does this services exactly expose the web server pods and leaves the other pods? Here is the answer. Kubernetes Services uses labels and selectors to match the correct pods that is running in the cluster. Take a look at the service definition here. The key attributes of a Kubernetes services are: first, selector. In the selector field, we will be specifying a label in the form of key value pair. This selector label should be matching with the pod label where we are intended to route the traffic. In our case, the selector label exactly matches with the web server pod labels, that is app equals web. Second, ports and protocol definitions. In the ports section, we will be defining the service port as well as the target port. Target port is nothing but our pod port number where our application is exposed. There are many types of services available, but for this video, consider the service type as cluster IP service. Cluster IP service is the default one if we did not specify any service type in the YAML manifest. This cluster IP service is resolvable only within the cluster. Once this service definition is applied in the cluster, this service will try to identify the pods that matches the selector label and maps those pods as its backend endpoints. In our case, it is the web server pods which is having the exact matching labels. So, whenever we hit a service IP with a service port number, the connection will get routed to the backend pods in the pod port number. Let us inspect the same service using kubectl command line utility. Using kubectl describe svc command, we can see that the service is assigned with a static IP address and its endpoint field is updated with the pod IP addresses. This pod IP will be updated dynamically whenever the pod is killed and recreated. But who monitors all these activities and who is assigning these static IP addresses to the services? Let us see the same in the next slide. Kube-Proxy and virtual IP management. Showing here is a Kubernetes cluster having one master and two worker nodes with all the necessary control plane components installed. It is the Kube-Proxy component that is responsible for implementing virtual IP mechanism for the services. It does that by allocating each service its own static IP addresses from or within the service cluster IP range CIDR. Remember that this CIDR range is a different one than that of the allocated pod CIDR range. We can see this range from the Kube API server process that is running in the master node. We can also override this range at the time of installing the Kubernetes cluster. To ensure each service a unique IP, an internal allocator automatically updates a global allocation map in the etcd database. This will be done before creating a service. This avoids collisions while leasing the IP addresses to the services. For example, if an IP address is already allocated to a service, then that particular IP addresses will not be assigned to a new service until the first service is deleted. Whenever a client hits this unique IP addresses, the connections will be forwarded to the backend pods. To enable this forwarding technique, Kube-Proxy uses packet processing logic on the OS kernel itself to transparently redirect the traffic to the backends. In other words, Kube-Proxy creates IP packet forwarding rules in all the nodes. So, whenever we hit this service, traffic will be forwarded to the backend pods which has got selected as a part of selectors and labels. Within the backend, selection of a particular pod is fully dependent on the proxy modes, which we will discuss in the upcoming slide. Kube-Proxy Modes. The Kube-Proxy starts up in different modes which are determined by its configurations. On the Linux nodes, the available proxy modes are IP tables and IPVS. IP tables uses IP packet filtering technique on the Linux kernel firewall to enable routing. IP tables is the default proxy mode for Kubernetes implementations. Kube-Proxy in IP tables mode chooses a backend pod at random. IPVS uses transport layer load balancing technique on the Linux kernel to enable the routing between the services and pods. IPVS provides more options for balancing traffic to the backend pods. They are round robin, least connection, destination hashing, source hashing, shortest expected delay, and never queue. With respect to Windows, kernel space is the only proxy mode available to configure packet forwarding rules in the Windows kernel. Well, that's it for this lecture. This is the summary that we have seen so far in this video. Thank you from VSPARKZ and thank you for watching this video.